All right, so yesterday we looked at Pythagorean theorem that we can use if we have a right triangle and we have two sides of the right triangle. We can find the third side using Pythagorean theorem. A squared plus b squared equals c squared. So now we're going to start looking at what are known as the trig ratios, trigonometric ratios. And they are the sine of an angle, the cosine of an angle, and the tangent of an angle. We can remember this relationship by the acronym SOHCAHTOA. S stands for sine, O for opposite, H for hypotenuse. The definition of sine is that it's opposite over hypotenuse. So we're going to learn about what all these things mean. The ka part tells you that cosine is adjacent over hypotenuse. A before H, adjacent on top, hypotenuse on the bottom. And the toa part tells us that the tangent ratio is the opposite over adjacent. Again, O first, A second. Opposite on top, adjacent on the bottom. So we're going to learn about these, and we're going to learn about how we use them.
In this video, I want to give you the basics of trigonometry. Trigonometry. And it sounds like a very complicated topic, but you're going to see that it's really just the study of the ratios of sides of triangles. The trig part of trigonometry literally means triangle, and the metry part literally means measure. So let me just give you some examples here, and I think it'll make everything pretty clear. So let me draw some right triangles. Let me just draw one right triangle. So this is a right triangle. When I say it's a right triangle, it's because one of the angles here is 90 degrees. This right here is a right. That right there is a right angle. It is equal to 90. It is equal to 90 degrees. And we'll talk about other ways to show the magnitude of angles in future videos. So we have a 90-degree angle. It's a right triangle. Let me put some lengths to the sides here. So this side over here is maybe 3. This height right over there is 3. Maybe the base of the triangle right over here is 4. And then the hypotenuse of the triangle. The hypotenuse of the triangle over here is 5. You only have a hypotenuse when you have a right triangle. It is the side opposite the right angle, and it is the longest side of a right triangle. So that right there is the hypotenuse. Hypotenuse. You probably learned that already from geometry. And you can verify that this right triangle, the sides work out. We know from the Pythagorean theorem that 3 squared plus 4 squared has got to be equal to the length of the longest side. The length of the hypotenuse squared is equal to 5 squared. So you can verify that this works out. This satisfies the Pythagorean theorem. Now with that out of the way, let's learn a little bit of trigonometry. So the core functions of trigonometry, we're going to learn a little bit more about what these functions mean. There is the sine function. There is the cosine function, and there is the tangent function. And you write sine, cos, or sin, cos, and tan for short. And these really just specify for any angle in this triangle, it'll specify the ratios of certain sides. So let me just write something out. And this is a little bit of a mnemonic here, so something just to help you remember the definitions of these functions. But I'm going to write down something. It's called SOHCAHTOA. SOHCAHTOA. And you'll be amazed how far this mnemonic will take you in trigonometry. So we have SOHCAHTOA. And what this tells us is, so tells us that sine is equal to opposite over hypotenuse. Opposite over hypotenuse. Opposite over hypotenuse. It's telling us, and this won't make a lot of sense just yet. I'll do it a little bit more detail in a second. And then cosine is equal to adjacent over hypotenuse. Cosine is equal to adjacent over hypotenuse. And then you finally have tangent. You have tangent. Tangent is equal to opposite over adjacent. Opposite over adjacent. So you're probably saying, hey Sal, what is this, all this opposite, hypotenuse, adjacent? What are we talking about? Well, let's take an angle here. Let's say that this angle right over here, This angle right over here is theta, between the side of length 4 and the side of length 5. This angle right here is theta. So let's figure out what the sine of theta, the cosine of theta, and what the tangent of theta are. So if we want to first focus on the sine of theta, the sine of theta, we just have to remember SOHCAHTOA. SOHCAHTOA. Sine is opposite over hypotenuse. So sine of theta is equal to the opposite. So what's the opposite side to the angle? So this is our angle right here. The opposite side, if you just go the opposite side, so not one of the sides that are kind of adjacent to the angle, the opposite side is the 3. If you're just kind of, it's opening onto that 3. So the opposite side is 3. And then what's the hypotenuse? The hypotenuse, well, we already know the hypotenuse here is 5. So it's 3 over 5. The sine of theta is 3/5. So someone says, hey, what's the sine of that? It's 3/5. And I'm going to show you in a second that the sine of theta, if this angle is a certain angle, it's always going to be 3/5. The ratio of the opposite to the hypotenuse is always going to be the same, even if the actual triangle were a larger triangle or a smaller one. So I'll show you that in a second. But let's go through all of the trig functions. Let's think about what the cosine. Let's think about what the cosine of theta is. Cosine is adjacent over hypotenuse. So remember, this, let me label them. We already figured out that the 3 was the opposite side. This is the opposite side. And only when we're talking about this angle, when you talk about this angle, this side is opposite to it. When you talk about this angle, this 4 side is adjacent to it. It's one of the sides that kind of make up that kind of form the vertex here. So this right here is an adjacent side. Adjacent. And I want to be very clear, this only applies to this angle. If we were talking about that angle, then this green side would be opposite and this yellow side would be adjacent. But we're just focusing on this angle right over here. So cosine of this angle, we hear about adjacent. Well, the adjacent side to this angle is 4. So it is adjacent over the hypotenuse. It's the adjacent, which is 4, over the hypotenuse. 4 over 5. Now let's do the tangent. Let's do the tangent. The tangent of theta. Opposite over adjacent. The opposite side is 3. The opposite side is 3. What is the adjacent side? We already figured that out. The adjacent side is 4. So knowing the sides of this right triangle, we were able to figure out the major trig ratios. And we'll see there are other trig ratios, but they can all be derived from these 3 basic trig functions. Now, let's think about another angle in this triangle, and I'll redraw it just because my triangle is getting a little bit messy. So let's redraw the exact same triangle. The exact same triangle. And once again, the lengths of this triangle are, we have length 4 there, we have length 3 there, we have length 5 there. The last example, we used this theta, but let's do another angle. Let's do another angle up here. Let's do another angle up here. And let's call this angle, I don't know, I'll think of something, a random Greek letter. So let's say it's xi. I know it's a little bit bizarre. Theta is what you normally use, but since I already used theta, let's use xi. Actually, even instead of xi, let me just simplify it. Let me call this angle x. Let's call that angle x. So let's figure out the trig functions for that angle x. So we have sine of x is going to be equal to what? Well, sine is opposite over hypotenuse. So what side is opposite to x? Well, it opens onto this 4. It opens onto the 4. So in this context, this is now the opposite. This is now the opposite side. Remember, 4 was adjacent to this theta, but it's opposite to x. So it's going to be 4 over, now what's the hypotenuse? Well, the hypotenuse is going to be the same regardless of which angle you pick. So the hypotenuse is now going to be 5. So it's 4/5. Now let's do another one. What is the cosine? What is the cosine of x? So cosine is adjacent over hypotenuse. What side is adjacent to x? That's not the hypotenuse. You have the hypotenuse here. Well, the 3 side. It's one of the sides that forms the vertex that x is at, and it's not the hypotenuse, so this is the adjacent side. That is adjacent, so it's equal to 3 over the hypotenuse. The hypotenuse is 5. And then finally, the tangent. We want to figure out the tangent of x. Tangent is opposite over adjacent. SOHCAHTOA. Tangent is opposite over adjacent. Opposite over adjacent. The opposite side is 4. I want to do it in that blue color. The opposite side is 4, and the adjacent side is 3. And we're done. In the next video, I'll do a ton of more examples of this just so we really get a feel for it. But I'll leave you thinking about what happens when these angles start to approach 90 degrees, or how could they even get larger than 90 degrees. And what we're going to see is that this definition, the SOHCAHTOA definition, takes us a long way for angles that are between 0 and 90 degrees, or that are less than 90 degrees. But they kind of start to mess up really at the boundaries. And we're going to introduce a new definition that's kind of derived from the SOHCAHTOA definition for finding the sine, cosine, and tangent of really any angle.
Okay, so what we use these trig ratios for, we use them to find missing sides and missing angles in right triangles. So far we just learned about Pythagorean theorem, which can only be used if you have two sides of a triangle and you want to find a third side. Okay, Danny? But what if we're only given one side and an angle? This is where the SOHCAHTOA, our trig ratios, come into play. But first we have to know how to label the triangle. So remember, the side across from the right angle is always the hypotenuse. That never changes. So in this triangle, the side across from the right angle is the hypotenuse. The opposite and adjacent are labeled according to what angle you're using, what angle you're working with. Maybe you're given that angle. Maybe you're trying to find that angle. Either way, that's the angle you're working with. And in this case, that is shown by angle theta. Theta is a Greek letter that's often used to represent an unknown angle. So because theta is the angle that we're working with, the side across from that is the opposite, and then the third side is adjacent. So we're always going to label our triangles this way. Start with the hypotenuse because that never changes. The opposite and the adjacent side, though, will change depending on what angle you're working with. And then once we have that, we can write our three trig ratios. Again, SOHCAHTOA tells us what the ratios are. The SO part tells us that sine is opposite over hypotenuse. Opposite first, hypotenuse second, which means opposite on top, hypotenuse on the bottom. The cosine, that's what the ka part tells us. Cosine is adjacent first, hypotenuse second. It's adjacent on top, hypotenuse on the bottom. And the tangent, that's the TOA part. It's opposite first, adjacent second. Opposite on top, adjacent on the bottom. And again, we're going to see how we can use these to find missing sides and missing angles in right triangles. So for this next example, let's write the three ratios for angle A and for angle B. We never use the 90-degree angle with SOHCAHTOA. And there's a couple different reasons for that. Okay, and we'll learn about that soon. It's always one of the two other angles that are between 0 and 90 degrees. So this is similar to the triangle that he showed on the video. It's a 3, 4, 5 triangle. The two legs are 3 and 4. The hypotenuse is 5. So we're going to start and first write all three ratios for angle A. So if I'm going to use angle A, I'm going to label the sides of the triangle. The side across from the right angle is the hypotenuse. That never changes. But now because I'm using angle A, I'm going to write the three ratios for angle A. The side across from that is the opposite. The third side becomes the adjacent. We're always going to label this way. Start with the hypotenuse. Then look what side is opposite the angle you're working with. That becomes the opposite. And then you're left with the third side to be the adjacent. Okay, so we're going to write the three ratios for angle A. So question B here is asking for the sine of A. Question E is asking for the cosine of A. F is asking for the tangent of A. We're going to do those ones first because we've got our triangle labeled from angle A. And remember that sine is opposite over hypotenuse. That's what the SO part tells us. And from angle A, the opposite is 4, the hypotenuse is 5. That's the sine ratio for angle A, 4/5. Okay, and then for cosine, cosine, according to SOHCAHTOA, is adjacent over hypotenuse. The adjacent is 3, the hypotenuse is 5. And tangent of A, well, SOHCAHTOA tells us that tangent is opposite over adjacent, which would be 4 over 3. So there are the three ratios from angle A. Now, though, we're going to do it from angle B. So if we're working from angle B now, the opposite and the adjacent sides will change. They'll switch. From angle B, the side across from that is now the opposite, and the third side is the adjacent. The hypotenuse never changes. It's always the side across from the right angle. So here's one reason why we never use the right angle with SOHCAHTOA, the 90-degree angle. If we say that we're going to use angle C, that would make the side across from it both the hypotenuse and the opposite. Hypotenuse is always across from the right angle, and if you say you're using angle C, that would make that side also the opposite, because the side opposite is the one opposite the angle you're working with. You can't have one side with two different labels on it. You can't say it's both the hypotenuse and the opposite. So that's one reason why we never use a 90-degree angle when we're doing SOHCAHTOA. But now from angle B, we can write the tangent of B, and SOHCAHTOA tells us that tangent is opposite over adjacent. So now it is 3 over 4. The side opposite B divided by the side adjacent to B. The sine of angle B, sine is opposite over hypotenuse, that'll be 3 over 5. And the cosine of angle B, cosine is adjacent over hypotenuse, that'll be 4 over 5. So you may have noticed that the sine of A is equal to the cosine of B. That's always going to happen. The sine of B equals the cosine of A. That will always happen. And the tangents are reciprocals of each other. That will always happen. We've only got three sides in this triangle, so there's going to be some values that are repeated. Also, I want you to note the sine and cosine of A and B are fractions that are equivalent to a decimal between 0 and 1. That will always happen. The sine and cosine of every angle between 0 and 90 degrees will always be a decimal between 0 and 1. Whereas tangent can be greater than 1. The tan of A is 4 over 3. That's 1.3 repeating. Okay? Try that one on your own, and then we'll check it. So if we started with angle M, the side across from that is the opposite. The hypotenuse is always across from the right angle. That never changes. The third side is the adjacent. So the definition of tangent is its opposite over adjacent. In this case, that'll be 12 over 5. So we'll do all three ratios for angle M first, and then we'll switch and do angle N. Part E says, what is the sine of M? Well, the definition of sine is its opposite over hypotenuse. That'll be 12 over 13. And then the cosine of M, that's the only one we're missing now for angle M. Cosine is adjacent over hypotenuse. That'll be 5 over 13. So there's the three ratios for angle M. Now we have to do angle N. So the hypotenuse never changes. But now from angle N, the side across from that becomes the opposite, and the third side is the adjacent side. The sine of N, sine is opposite over hypotenuse, that'll be 5 over 13. The cosine of N, cosine is adjacent over hypotenuse, that'll be 12 over 13. And the tangent of N, tangent is opposite over adjacent, that'll be 5 over 12. Once again, the sine of M equals the cosine of N. The sine of N equals the cosine of M, and the tangents are reciprocals of each other. The sine and cosine are all decimals between 0 and 1. However, the tangent can be greater than 1 because the tangent of M is 12 over 5, which would be 2.4. Okay? So before we start using these to solve problems, we need to be able to use our calculators with sine, cosine, and tangent. Since all angles that we will encounter will be expressed in degrees, we must be in degree mode. So, all scientific calculators have sine, cosine, and tangent. So you should see them on your calculator. SIN is sine, COS for cos, TAN for tangent. And you have to be in degree mode. So usually up in the window, there'll be a display, or you might see the letter D for degrees, or DEG for degrees. If it says R or RAD for radians, it's in the wrong mode. Or if it says G for gradients or GRAD, again, it's in the wrong mode. You need to be in degrees. So on these Texas Instrument calculators, the mode key is at the top here, and my calculator is in degrees. So I'm good. Now, to make sure that your calculator is in the right mode, if you take the tangent of 25 degrees, it says calculate each of the following to 4 decimal places. The tangent of 25. So for most calculators, you're going to hit the tangent key first, and then type in your angle, and hit enter. The 4 decimal places is 0.4663. That's your answer. Now, if you're not getting that, it could be one of two things. Either you're in the wrong mode, or maybe some of the older calculators or different ones, you have to put the 25 in first and then hit the tan key. Okay, but if you put tangent first and 25 and then hit enter, if you don't get 0.4663, something's the matter. So everyone should be trying that right now. You're not getting that? Bring it here. Yeah, I did it. I went tangent and then 25 enter. It works. Everyone else is good? Okay. So then for the sine of 42, it's sine of 42 enter 0.6691. Yes. Bring it here. So sine of 42 enter. Yeah, so something is wrong here. Looks like it's in degrees, but you're in fixed decimal. So let's see if we can change that. And when you do the tan of 25, did it do the same thing? Yeah, it did round it. So stat data. Let's try this now. Tan of 25. There we go. Okay, yours isn't working? Let me see. Okay, you're a scientific. We don't want to have that. Mode normal.
I went to 10, and 10.25, and I got 4.6 with 1.66.
Yeah, it's in scientific notation. I just got to find out how to change that. Setup. 0. Okay, now it's fixed.
Thank you.
All right, and then the cosine of 68 degrees is 0.3746. All right, so here's how this works. So many years ago, mathematicians were fooling around with right triangles because there were no good shows on TV or anything like that. But they found something interesting happening, and that is that they worked with similar triangles. Now, similar triangles have the same shape but are just different in size. Okay, Keen? So what that means is you can draw lots of different right triangles that, let's say, have a 46-degree angle in it. They can make it bigger and smaller, so the lengths of the sides are changing, but the angles are staying the same. Those are called similar triangles. So that's what they did. They started messing around with similar triangles. Triangles that had the same three angles, but were just different in size. And every time they took the ratio of the sides, they got the same decimal. So one of those triangles they messed around with was a triangle that had a 25-degree angle in it. So the other angle would be 65 because the three angles add up to 90 degrees always, right? So, but they started with that angle of 25 degrees, and they had a bunch of different triangles that were different in size but had the same shape. They all had a 25-degree angle and a 90-degree angle, and the third angle was 65 degrees. But when they started measuring the sides and taking the ratios of those sides, they always got the same decimal. When they took the ratio of the opposite over the adjacent from 25 degrees, they always got 0.4663 every single time. And so they gave that ratio a name. They called it the tangent. And your calculator has these values programmed in. When I first started high school, we didn't have scientific calculators. So we had a trig table. And so it had every angle between 0 and 90 degrees. It had three columns for sine, cos, and tan. And you look at your angle on the left across to whether you wanted sine, cos, or tan, and it gave you the decimal, the four decimal places. Now calculators have all these stuff programmed into them. But this is where they came from. Mathematicians discovered that if you had a 42-degree angle and you took the ratio of the opposite over the hypotenuse every single time, they got the same decimal, 0.6691. And they gave that ratio a name. They called it the sine. And same thing with cosine. So that's where these values came from, right? From doing investigations and research into working with the sides of the right triangles. So we're going to see two different types of questions, okay, Shyla? One where you're given an angle and you're going to use that to find a side, or maybe you're given two sides and you want to find an angle. So up above in example 2, we were given the angle. We found the tan of 25, the sine of 42. and the cosine is 68. And we rounded it to 4 decimal places. But sometimes you're trying to find the angle. You're told what the sine, cos, or tangent of an angle is as a decimal, and you want to work backwards to find the angle. So to do that, that's where we use the sine to the -1, cos to the -1, and tan to the -1 functions, which are above the sine button, above the cosine, and above the tangent. If we're told the tan of theta is 1.2115, and you want to know what theta is, theta can be found by going tan to the -1 of 1.2115. So you're going to go second function tan in your calculator, and then you're going to type in that decimal, 1.2115. And if we round that to the nearest degree, we would get 50 degrees. Theta is approximately 50 degrees. So you're either going to be given the angle or you're trying to find the angle. If you're given the angle, you're just going to use the sine, cos, or tan keys. But if you're trying to find the angle and you're given what the sine, cos, or tan is as a decimal, this is where we use the second function, the sine to the -1, the tan to the -1, or the cos to the -1. So you're going to go second function tan, and then type in that decimal to get theta. So question B, if the sine of beta, that's just a Greek letter, is 0.4771, and we want to find out what angle beta is, we can find that by going sine to the -1 of 0.4771. Second function sine of 0.4771. So to the nearest degree, that would be 28 degrees. That's the angle, such that the ratio of the opposite over the hypotenuse will be 0.4771. And then for the last one, if you're told that cosine of gamma, that's another Greek letter, is 0.7225, if we want to find out what gamma is, we'll go cos to the -1 of 0.7225. Cos to the -1. So second function cos of 0.7225. So to the nearest degree, it'll be 44 degrees. So either going to be given the angle, and we will use that to find another side, or you're going to be given two sides and you want to find the angle. Those are the two types of questions that we're going to be working with. So this next one says determine cosine of 56 degrees. So you're given the angle of 56. You want to find the cosine to 4 decimals, so it'll just be cos 56, enter, 0.5592 to 4 decimal places. 0.5592. And part B says determine theta to the nearest degree. If the tan of theta is 0.3915, and we want to find out what theta is, we're going to have to go tan to the -1 of 0.3915. So second function tangent of 0.3915. Approximately 21 degrees to the nearest degree. Okay? Example 4 says draw a triangle to represent that tan of theta is 5/4 and then calculate angle theta to the nearest tenth of a degree. Remember that if we're using SOHCAHTOA, if we're using Pythagorean theorem, we must have a right triangle. So we'll draw a right triangle here. And our right angle obviously is in that bottom left-hand corner, the way I drew it. And now we have to designate one of the angles to be theta. It doesn't matter which one of the other two angles are theta. It can be the one at the top or the one at the bottom. It doesn't matter. So I'm just going to choose the one at the bottom. Now, if we label the sides of the triangle, the side across from the right angle is the hypotenuse. I've designated that that bottom angle on the right is theta, so the side across from that is the opposite. The third side is the adjacent side. And we are told the tan of theta is 5 over 4. Well, SOHCAHTOA tells us that the tangent ratio is opposite over adjacent. That means opposite on top, adjacent on the bottom. This ratio of 5 over 4 has the 5 on top. That's the opposite. It has the 4 on the bottom. That's the adjacent side. So for the triangle that I've drawn and for the angle theta that I've designated in that bottom right-hand corner, the side across from theta must be 5. The side that's beside theta has to be the 4 because tangent is opposite over adjacent. Then it also says, what is theta to the nearest tenth of a degree? So this is exactly like question B above. You're told what the tan of theta is. You want to find out what theta is. The only difference is that in this case, we're given tan of theta as a fraction instead of a decimal, but it doesn't change the way it's done. Theta can be found by going tan to the negative 1 of 5 over 4. If you want, you can go 5 divided by 4 first and get a decimal, 1.25, but you don't need to. You can go straight to the calculator and just go second function tan of 5 over 4. The calculator will divide 5 over 4 as a decimal, and then go second function tan of that decimal, 51.3 degrees to the nearest tenth. So there's the angle theta to the nearest tenth. Okay, so we'll stop there. Tomorrow we'll actually start working with these trig ratios to find the missing angles. So I'll hand out the assignment and I will post the solutions on Google Classroom. Again, it's important that you do the practice.